Is my screen visible?
Yeah, Diksha.
Hello everyone and welcome to Formula Bharat Driverless Workshop 2023. The topic for today's session is path planning and trajectory control for autonomous vehicle hosted by MathWorks. The topic will be represented by Veer, student program application engineer at MathWorks. All participants are requested to note the following general instructions. We encourage you to turn on your video during the session. Please mute your microphone throughout the session unless you have asked otherwise and during the doubt solving session. Without further ado, let's begin with the session. Over to you, Veer.
Yeah, Dikshita, thank you. And yeah, let me know if you all can see my screen. So you can confirm once. Is it visible, my screen?
Yeah.
Okay, perfect. Okay. So yeah, before we get started, I mean, like, there are only few people, but still I wanted to understand, like, what's your background? Like, are you a student or you're working or you're part of a Formula student team? Because Formula Bharat is basically for the Formula student teams. And a lot of times, like, whenever we do the session, it is more inclined towards the Formula student teams. But if you can give me some background, that will really help us to understand, like, from where are you coming from?
Hi, Alexandra. This is Shrikant. So I'm
Hi, Shrikant.
working at I'm actually working professional. So I'm working at ZF Commercial
Okay.
Vehicle Control Systems.
Yeah, nice to meet you, Shrikant. Thank you.
Yeah, myself, Nitin. I'm a student at VIT. Hello.
Okay, nice. Okay, then thanks for confirming.
Hello, Veer. I'm Kaushik from Hercules Racing Team. So, yeah, we have met before during the FST event.
Okay, awesome. Okay, great. So, okay, fine. Okay, I won't push everyone to talk. It's completely fine. Okay, so I'll get started. So this is one of the, like, on the screen that you see is this is one of the project that we did with respect to create some content around trajectory tracking controllers. That's a vehicle is driving on a highway. And you can see there is a nice scene in, this is a scene in Unreal created using Roadrunner. So that was done. I think the one session that we did was the first session where we spoke about the scenario creation and scene creation, and that like how it can be exported into Unreal and different gaming engines to interface with the full vehicle dynamics model. And further, if you want to expand that model with respect to some perception algorithm path planning, you can do that. So this is example which is consisting of vehicle dynamics model along with trajectory tracking controller, and then we have integrated it with the Unreal scene. So since the topic is basically, we're going to talk about the trajectory tracking controller, and one path planning example I'll just talk about, which is specific to the Formula student teams. So that we'll go through, but at the same time, I'll show our webpage that what other functions we are supporting in terms of path planning. Okay. So with this, let's get started. So just a background. So my name is Veer Alakshendra. So I've been in MathWorks for more than 6 years. So I completed my PhD in robotics. And then after that, I mean, during that period, I used MATLAB simulating and different multiple toolboxes, tools to solve my PhD problem statement. And after that, directly I joined MathWorks. So I started my career here as automotive specialist supporting the global automotive competitions. Still, I'm doing that. I mean, like I'm supporting the global automotive competitions such as Baja, Formula Student, and Formula Student, like different Formula Student in India, UK, Germany, and all. And the core part of my role was to generate content. And like if you search on YouTube, so me and my team, we have published multiple number of videos with sort of like getting started for students so that how they can use MATLAB and Simulink for automotive for applications. And now I'm also leading a team in India. So we have a team of a total 5 members supporting different student programs. So with this, let me go through the agenda. So agenda is quite simple. I will talk about a path planning demo. Nothing like theoretically, I'm going to get into that, but more on the application side of the Formula Student in Germany path planning, like how do you do it? Because in this competition, we understood that all those various path planning approaches, which is there in the theory, may not be applicable for such kind of applications. So I'll go through that, and I'll also show the web page where we are showing what are the different other path planning algorithms we are supporting. Then quickly, I'll go through a vehicle dynamics model, because if you're building a trajectory tracking controller, you need a vehicle dynamics model. And then I'll go through different tracking algorithms, Pure Pursuit, Stanley, MPC. And then we'll just talk about key takeaways, resources. And in between, if you have any questions, feel free to ask, because we don't have like a lot of people over here. Most of them are having exams and all. So they'll be watching the recordings, but if you have any queries, you can just chime in. So what I'll do is, without wasting time, we have a live script actually built using MATLAB live script, okay, where we are solving a path planning problem. Okay. So this is a path planning algorithm for specifically meant for if you have object detected on the left and the right side of the road, how do you plan a path out of it? So what we have done is, using certain functions and simple triangulations, we have built this solution. Now, why we did that? First is that we got the motivation from the students, because there were other like tree-based approaches which teams have tried. But when it comes to deployment and actually running a race car autonomously, one thing is very important, that which hardware you're deploying the code. If the code is very complex, and then you have to, on that hardware, which are like, I think Jetson is one of the common ones students use. Now they're evolving, they're also looking into different other hardwares. So what happens is that you have to run all the other algorithms as well, like SLAM you have to run your path planning algorithm, you have to run the trajectory tracking, you have to run the perception algorithm. There are multiple autonomous algorithms that you have to run. So whenever you're building a path planning algorithm, you have to make sure that actually it is going to go on a vehicle, so that should work. And in this case, for the Formula Student and the racing competition, it is quite I would say complex, because the vehicle has to race and it has to improve the lap time. So what we'll do is, let me go back, and I have my script open. One second. Okay, yeah. So this is the script which is again available, but I'll talk about that how just by using simple functions, simple understanding of triangles and math, you can build a whole path planning algorithm for these kind of scenarios. Now, in this one, for example, like even if you're not from the Formula Student or racing competition, autonomous racing competition, to just give a brief of the problem statement, that you have a car, and then you have some blue cones and some yellow cones. So this path planning will come once you have detected all these objects, of course. So in this one, we are assuming that your detection is proper, like you're 100% detecting all the cones and you're not missing any of the cones. And if there are any outliers, you're neglecting those, or you have removed those outliers if you have. So that's what the problem is. And then what the vehicle has to do is, based on the position of these cones, it has to find the path through it. So again, assumption is that it has, through the perception algorithm, we are knowing that, okay, which are the objects. And after that, we have the algorithm written for which are the blue ones, which are the yellow ones, and what are the coordinates. Okay, so this is just only the path planning that we are planning over here. So what we are doing over here is we are using a certain concept called Delaunay triangulation. Okay, so basically the criteria says that for a set of points in 2D, a Delaunay triangulation of these points ensures the circle associated with each triangle contains no other point in its interior. For example, if you see here in this case, like, okay, let me open the one with, like, these are the triangles, okay, formed because of these vertices V1, V4, and V2. This one, and then you have similarly you have V4, V3, and V2. Okay, so here both like T1, T2, what we are seeing are falling under the Delaunay triangulation, or you can say these triangles are Delaunay triangulation. Whereas if you see the next example over here, in this, when we are forming the circumcircle, there is a point, there's a vertex which is falling inside the circumcircle. So in this case, these two here, what you see, these are not a Delaunay triangulation. So basically, you have to just form a circumcircle based on the vertices that we have. And then if there is no point inside that, then it is a Delaunay triangulation. If it is there, it is not a Delaunay triangulation. Okay. So with this, just a basic understanding of what Delaunay triangulation is, like what we have come up with a simple basic approach, which is also being used by multiple teams. So we have been judging multiple teams across the world, and we are seeing that students are kind of following this method to kind of interpolate, to kind of find the path through these two cones. So first, what we do is, for example, over here, that we use certain functions to create the Delaunay triangulation for certain set of yellow cones and the blue cones. And then what we do is we remove the exterior triangles. Now, again, here the approach could be that if you want to write your own code, even to remove the exterior triangles, it can be done. But there are certain functions which are built-in functions in MATLAB, which can help you kind of remove this exterior part, remove the exterior triangles. And then finally, we find the midpoints. So what we do is that we have these vertices connected by triangles, and then we find the midpoint, and then we finally interpolate. Okay, so this is how we plan the path. Now, going in detail through each of these steps, what we are doing is first we load the coordinates, as I mentioned that, okay, we are assuming that the perception has been done. So in this case, what we did, the detection that we did using YOLO, and we have found the coordinates and the different blue and the yellow codes. And then there are some kind of pre-processing the data, because when we are using the built-in function, which is there for Delaunay triangulation, there is certain kind of format that we have to consider. So that's what we have done is that we had the inner cone position for the yellow and the blue ones. And then we have merged it alternatively, like by yellow cone, blue cone, yellow cone, blue cone. This is the, like, after, once we have the coordinates. Okay, again, this is not necessarily, and this is not necessary. It is just being done here because the function requires that that there should be arranged in alternate ways. Once that is done, then using the Delaunay function that we have, which is called Delaunay triangulation, we are forming the triangles. So over here, you can see that. So we have, after arranging in alternatively, we have total 4 over here, 4 vertices, and then we are forming the Delaunay triangulation. So this is the triangle that we get. Okay, so again, this is the function, this is the built-in function which we are taking advantage of. Okay, and then further, the function that we have, then you can extract different properties out of it. Like, for example, here we have to remove the exterior triangles. So for that, okay, here I can also show that once we run the program, how does it look like the Delaunay triangulation? Let me run it once. Okay, it's running. Meanwhile, I'll go through the steps. So what we do is we remove the exterior triangles. Again, to remove the exterior triangles, we have certain functions, and we are removing this kind of triangle. For example, that if we take these many triangles, and again, there will be a Delaunay triangulation formed, because again, there are 3 vertices. So it is forming a triangulation over here as well. Now, if we keep this, then of course, like the path may be disoriented or deviated, and it can go from here to here. So there are multiple approaches. One approach we have showing over here is that we are removing the exterior triangle. Another approach could be that using different properties, you can form a bound. So you can form a bound between this one and that one, and then you can mention in the code that, okay, I have to pick the sides only between these bounds. So that can also be possible, but we are actually using the function properties. So for that, what we do is we define the constraints. Okay, so there's a certain format. So we are defining the constraints over here. And then we are using a certain create Delaunay triangulation with constraint function that is over here with constraint. So Delaunay triangulation with C is basically mentioning the constraint. And once you do that, what happens is that you basically remove this triangle, and finally you get some triangles like this, like removing this part. Okay. And once you have removed it, so this is how it looks like once you have used all these functionalities and you have removed it, this is how it will look like. So this is the triangle that we'll get, okay, after removing this. Now, after this, it is quite simple. Reason being that that you have all the set of different sides, and you just need to find the midpoint out of it. Now, many a times what happens is that students ask that, okay, why we are doing so much complications forming triangles? Why we can't just have straight lines between this? So if you do that, the problem will be during the turning. So if you're turning it, in that case, you might miss some of the points, because every time you're not able, if you, for example, if you're missing some kind of cones, you might miss some of the sides. Okay, and in that case, maybe there might be some deviation. So this was the image which is showing with all the exterior triangles over here. You can see that this is forming different exterior triangles. So this is the one way. And then if you go down further, okay, so we have done all this part. And after that, once you have removed that using different functions, this code is available, no worries, like you can have a look into that. Then what we do is, once we have this, we just find the midpoints out of it. Again, there are like simple ways to find the midpoints. There's odd and even ways I have mentioned over here in the code. And once you do that further, we do the interpolation. So this is the final thing that we get over here. This is what we get. Now, this code has certain limitation. The limitation is that already we have assumed that if there are any false positives, we have removed it. But if you run on the actual track, it might happen that your perception algorithm might miss some of the counts, or there could be some false positives. In that case, you have to improve the code. So that, I think, that's also something that we haven't done as of now, but that's not a big deal, because once you have the false positives, again, you have to accordingly mention the constraint. Okay, once you mention the constraint that this is our constraint, we have to be in this bound. So in that case, you can get rid of all the false positives, or if there are any outliers, which is by mistake if it is detecting those points as a code. Okay, so this is one kind of solution that we have come up with a formula for the formula student competition. Now, this can be further improved. There can be a lot of optimization can go on to this, and then you can also have a race time optimization. I'm not going in detail into that because we have limited time. Okay, and already it's 5:58. But nevertheless, can I ask someone, like, for example, like if you are a little bit aware of different other generic or popular algorithms, like there are graph-based algorithms, there are hybrid. A-star is one of the common, like very famous algorithms in robotics as well. And then under that, we have RRT star. Or in the layman's word, I can say these are like tree-based approach, which will form different nodes. And in that, between that node, it will try to form a path out of it. Can anyone answer that? Why in such scenarios like this, like why students or the teams, even the popular, the strong teams that we have seen, like top teams of world, we see that like they mostly rely on these kind of triangulation method. And then why not these? Why not these A star or RRT star, the different path planning algorithms that we have? Do you have any idea? Like do you want to share anything?
Time complexity, maybe?
Sorry?
Time complexity.
Yeah. It's basically the computational complexity. Yes, that's a problem. That's a major problem. So, and also that, I mean, the one that we saw, I think, few years back, there was someone who was using the RRT star, and the code was really good. It was, I would say, like it was really working. Like, for example, if you take a simple occupancy grid, so it was forming all the different nodes and trees, but if you see that it is creating so many nodes that it can be computationally complex, and then you have limitation on your hardware. Okay, so this is the reason, like one of the major reasons that students are going for this triangulation method. But this was a approach that the one that we saw. It is very simple, basically simple approach, but you can like definitely improve it. So what I will do is, so this code is available on our webpage. Okay, we haven't yet published on GitHub this one, but this was in the form of a full blog. So if you want to have a look, or if you also want to open it in MATLAB online, so you can have a look. So all these blogs that we publish, so this all has a function like feature to open it in MATLAB online. So this can be opened. So this is the button that you will get, run in browser, download live script. So you can download from here, or you can run in MATLAB online. Okay. So any question, any other question you have? If not, I can go to the next part, and then we can start talking about the VD part and the trajectory tracking controllers, which are mostly the common ones that are mostly used in autonomous driving, and how the tools are providing quite easy workflow to implement that. Okay.
I have one question about the deployment. So let's say if I developed or if I'm reusing the Delaunay triangulation method, what shown in the web page. So if I want to flash in my hardware, like generally what is the recommended approach? Like usually whether it's flash in hex format, or does it have any MathWorks specific extension for which we have to take care of some additional steps?
Okay, so that I would say, for example, Kaushik, I think we are talking about the code generation part. Okay, so for example, like if you have a simple code, anything like, for example, a robot, and you have to deploy an Arduino or RPi. So in that case, you don't have to do much. It's just that you have to use the MATLAB code generation capability. In that, for different hardwares, we have provided the support packages. For example, if you want to deploy on your Jetson code generation. Okay. So in that case, you just need to use this code Jetson support package for MATLAB coder. Okay, so this is a support package which will be installed, and then you can directly just flash, or you can deploy the code over that. This is one way. Okay, using the code generation capability. Other than that, if you just want to generate the C++ code out of it, so that also can be done. For that, again, you need to use the code generation. For example, if you have a model in Simulink, you can use a Simulink coder. However, there are few limitations. For example, all these functions that you see, most of them are code generatable. Okay, that the code can be generated and you can deploy to your hardware. But for the Delaunay, I think there are few functions which are not code generatable. For example, if there are certain functions which are not code generatable, there you might have to change a few things to make it code generatable. So for example, in the Delaunay function, there's one function which is not code generatable. That you might have to change, or maybe write your own code. So if you write it from scratch, so that can be code generatable. So that is one of the limitations of the code currently, I would say. Okay. So this one. Okay, so I think I'm forgetting the function that we used over here. There was one function which was not letting us generate the code. Okay, otherwise, most of the functions which are there that can be done. So it will be using the MATLAB coder and Simulink coder. And if you are using some kind of standard boards, so you can use the support packages to generate the code out of it. I'll do one thing. We recorded a full tutorial series for students, or I mean anyone can do it. It's a full series on the code generation capability. So it will also explain you what are the file formats that you get. Okay. And once you generate it and how you can edit those files. So those information you can find in the full training and you can put it.
Yeah, that would be great.
Yeah. So yeah, so this is the full online tutorial that we have, and this is in-depth a tutorial. Okay, so you can see over here. Okay, so it starts with code generation with MATLAB and preparing customizing generated code for MATLAB, then code generation with Simulink, and then again how to customize. For example, you have all the hex files and all, how you can customize it. And then finally, we have also shown a deployment part over here. Okay, so this is the one.
Okay.
Okay. And in the last part, in the last webinar, we covered this YOLO algorithm deployment on Jetson Nano. Okay, Jetson. This also you can have a look. Yeah, this was the NVIDIA Jetson video content that we covered the last session. So you can have a look into this as well. Okay, yeah, I hope this will help you.
Yeah. Thank you so much.
Yeah, no problem. Okay, so I'll move ahead. Okay, so yeah. Now that we have, we have to implement a trajectory tracking controller. So what we need is we need a vehicle dynamics model. So to do that, so I think if you're aware of MATLAB and Simulink, if you have used it, there are like multiple people want to build it from scratch. So based on the equation, they convert the equation into a certain, in a model, and then they move ahead with different applications. Now, to ease the process or to quicken the process, what we have done is we have come up with a toolbox called Vehicle Dynamics Block Set, which can be flexible to any of the applications. For example, if you are participating in autonomous competitions or looking into autonomous vehicles, in that case, if your focus is just to generate a virtual sensor data and high-level software studies, you can build that a simple model. Or in other case, if you have, for example, if you want to build a autonomous car with proper vehicle dynamics study based on different wheel forces, or you can say a high-fidelity model, that also you can do, through which you can get the longitudinal, lateral, and yaw motion. Okay. Now, how to solve this? So one method is, as I explained, that okay, you convert the set of equations into a model. Or what we have done is that we have provided a block set which is called vehicle dynamics block set, which is consisting of different pre-built blocks where you just need to define the parameters, and then based on certain inputs, you will get the expected output that you're looking for. So this is called vehicle dynamics block set. So it consists of library of blocks, powertrain, wheels and tires, steering, suspension, vehicle body, vehicle scenarios, and utilities. Then it also has pre-built scenes. For example, when you are looking for autonomous driving, you are going to create some kind of virtual scenes and scenarios. So we have already added certain pre-built scenes, but if you want to build some custom, that can also be done. So that we explained it in the first session, that was using the Roadrunner. And then we have also added certain examples which you can refer, or you want to just kind of do some virtual testing, you can change the parameters or parameterize the whole model and you can perform the virtual testing. And then what we'll do is we'll just, first of all, look into certain blocks and we'll see that how like you can build a simple model to a complex model in these kind of vehicle dynamics blocks. So let me open that. I'll close all the other things. Okay. Yeah. So for example, if I just open the simple one, over here. Okay, so this is just a simple model. So in the library, let me go through the library that we have. And I'll undock this. So over here, you can see that we have all these different sections. Okay, so vehicle body, you can find the vehicle body over here. You can have a 6-DOF model or you can have a 3-DOF model over here. Similarly, we have different suspensions, steering, powertrain, and tires. So for example, if you just want to collect some kind of synthetic data, so you have built a model and you want to simulate it in some kind of Unreal environment. So it is quite simple. For example, these are different blocks, and what you can do is you can simply just, based on steering input, you can run the vehicle in a simulation environment. I'll come to that simulation environment which I'm talking about. This is how to do it. Okay. Now, this is a sort of a very basic model, I would say. Like it doesn't have like much of the information. Further, if you want to have a look into like build some kind of more complex model, so it can be something like this one. So over here, like we are going one step ahead. So in the earlier model, we have the vehicle body 3-DOF model. So if I double click on this, so this basically this model lets you choose the option that how like well defined you need the model to be, or the vehicle dynamics model to be. Whether you just need the external longitudinal velocity, which was the last one, or you want just the longitudinal forces in the tire, or you want both the like FX and FY tire forces over there, which is could be a more detailed model. And then further, you have these other parameters that needs to be defined: longitudinal, lateral, yaw, aerodynamics, environment, and simulation. Okay. And then going ahead, then we have a steering system, which was also earlier. And then what we have done is we have added a simple model over here, a simple powertrain over here, which is comprising of one simple longitudinal wheel disc brake. And then we have a simple equation-based powertrain that we have used. Here, we are not using any block set. It is just a simple based on the power calculations. We have a simple powertrain, which is giving you the axle torque. And then we are just using a rear wheel drive and sending the axle torque to the tires. Okay. And now again, here also what you can do is that based on your steering, acceleration, and deceleration, you can run the model. Okay. So basically the whole point is that whether you want to create a simple model or you want to create a more high fidelity model, so that can be created in this using this block set. Now, for example, if I go inside this vehicle body part, okay, so let me get inside this. Once again, let me minimize. Yeah. So all these bodies or blocks that we see, these are all like open. So you can go inside it and you can finally look into what all these, how we have built this model. But more than that, you can also have a look into the help document, because this help document will make you understand that how we are building this block using different equations. Okay. This is the whole documentation that we have provided. So this will help you understand that there are different multiple input and output ports. So whether it is a vector, whether it is a matrix, whether it is a 3x4 or 4x3 matrix, it will help you understand that how you have to input the data, or not input the data, how you have to input the signal. Okay. Now, further, for example, if you want a very high fidelity model, like for example, if you want to include each and everything in your model, it should be a 6-DOF model, it should be having a controller, it should having a full complete powertrain. So let me open that one more. So in here, when we go to the vehicle dynamics block set, in the examples, if we open the constant radius or double lane change, whichever you want to see, this will open this model. Okay, so now you can see that if we enter in this passenger vehicle subsystem, so this has engine, this has transmission, driveline, and brakes, which is in detail. Okay, so here we are using the kinematic steering. We have a suspension, sorry, we have a transmission, which is a fixed transmission over here. Okay, and further, you can also, sorry, have a driveline model. Okay, so this driveline model looks like this. Okay. So this is active differential that we are using. And we have also mentioned the torsional compliance and for both the parts, for the XL1 and the XL2. Now, this is just giving you references that you can, based on the fidelity of the model that you require, you can build the model. If you're learning, if this is your first time, the suggestion would be just to start simple, build simple models, because in that case, you will be able to build more and more, you will understand the whole concept of modeling using these toolboxes, and further that can be used as an advancement to more high fidelity models. So what I'll do is, now that you have an overview of the vehicle dynamics model, now we'll see that how you can build trajectory tracking controllers just by using simple blocks. I mean, before that we get into that, you have any questions, you can please feel free to ask. Okay, if you don't have, no worries. Do you know what are the different types of trajectory tracking controllers? Or have you worked with any of the trajectory tracking controllers earlier? Or you are still in the exploration mode and you are learning what are the different trajectory tracking controllers?
I know about model predictive control.
MPC. Okay. Fine. Okay. Thanks for just answering that. Okay. So what we'll do is we'll go step by step. So for example, there are three popular trajectory tracking controllers, and then we have also your favorite PI controllers, but we are more talking in terms of a steering control, how if you want to control the steering, how you do that. So first one is a pure pursuit controller, and then is a Stanley controller, and the third one is the MPC controller. Now pure pursuit and Stanley controller, these are both geometric controllers. Then in pure pursuit, the limitation is that it is good for robotic applications and even Formula Student applications as well, but you need to tune it properly. Okay, and it doesn't account for the dynamics of the vehicle. So what it does is, it is again a path tracking algorithm, geometric algorithm. It calculates the trajectory of the curvature, and then for a vehicle, it computes the wheel steering angle to follow a reference trajectory. Now, this is one of the simplest trajectory tracking controllers. Even if you're not using certain block that we have provided and you're just writing the equations, you can do that. So in this one, what happens is that there are one of the governing thing over here is a look ahead distance. Okay, so if you have the look ahead distance smaller, it will the path will be oscillatory, but it could be accurate, but it will be oscillatory. However, if it is the look ahead distance is large, in that case it will be less oscillatory, but it might not track the trajectory properly. Okay, for example, especially during a larger curvature near the corners. So in here, for example, just to explain you like what is a formula of it. Like this is your figure, okay, and in this one you have this RRR, and this is the radius, and then you have this alpha, which is the target direction angle, and this is LD is the look ahead distance. So how you're selecting this, or how are you tuning this LD or look ahead distance, this plays a major role in tracking the trajectory based on pure pursuit controller. Okay. So a simple formula, this is the steering angle formula, means steering angle tan inverse of 2L sine alpha by LD. You can see that the formula is just based on geometry, simple geometry over here. Okay. Now to implement that, so what we'll do is we have created certain waypoints. We won't get into this like how we have created the waypoints. It's just that XY or the pose we have defined for this. And then we have built the vehicle model, controlling in Simulink, and then we have also integrated with the Unreal Engine. Okay, so how to use this or how to implement this, that is based on the libraries that we are using over here in this case. Okay. So for example, like these all can be found if I go into our robotic system toolbox. Okay, over here you can see that in the robotic system toolbox, you have this pure pursuit controller. Now, let me do one thing. I'll just call this one block and we'll see that what it requires and what are the input and the output. Okay. Okay, so this is our block, okay, that we are calling as a pure pursuit block. So this is accepting the pose X, Y, Z, and then we have the waypoints, and then it is giving the linear velocity and the angular velocity. So if you see over here that it is only giving the linear velocity and the angular velocity, but in our case, what we also want to show it or to get the target direction. So, and once we activate this one, so this will give you the target direction output port. And then you need to define certain parameters, in which one of the parameter over here, you can see that the look ahead distance, like what is the look ahead distance that you have to mention over here. Okay. Now to build this using the vehicle model, using the blocks in vehicle dynamics block set and the pure pursuit block, it's quite simple. So let me open this simple model. So over here, you can see that we are using the same vehicle body 3-DOF model, okay, which we used earlier. Then we are just having a pure pursuit controller block and a waypoint block and a visualization block. So in the pure pursuit controller, what we did is we have used the same block, defined the look ahead distance, and then we are converting the target direction into the wheel steering angle. So for that, we are using the same formula, that is this one, tan inverse 2L sine alpha by LD. So you can see over here that alpha, which is the target direction, we are getting it from this block directly. Okay, and then we are just converting it into the wheel angulation. And then further, we are sending it using just a concatenation because it requires in a certain vector form. So that's what we are converting it into. And then further, we are giving it as an input to the vehicle 3-DOF block. And then currently we are just running it with a constant velocity. And then we have this pose, like initial pose, that we need to define that from where the vehicle is going to start. Okay. Now, if I run this, you can see over here that now it is exactly tracking the trajectory control. Okay. Now, for example, if I change the look ahead distance, okay. So let me change that. So currently, what is it? Let me see. Okay, sorry, it was already there. So it is 5 now. Okay. So if you remember, we told that if it is too short, too less, it will be a little bit oscillatory. Okay, so let's try that whether we are getting that or not. So I'll do one thing. I'll make it 4. Sorry, -4. That will be 1. Okay, and let me run this. Okay, so you can see over here that it is now oscillatory. So similarly, now if I make it larger, for example, if I make it larger, so what would happen is that it will be smooth. It won't be oscillatory. However, it will miss the target. It will miss the trajectory. So again, running this. Okay. So I think this works with still 9 value, but I make it much larger. For example, 15. Let's see what happens. Okay, some deviation over here you can see during the curvature part over here. Okay, so the whole point is that, so this is the thing is that it is a very simple model. If you see over here, it is just like a toy model or a robot model. Like in robot, we are not much concerned about the interaction with the wheel and the road surface. Okay, and it is just moving with a constant velocity. Now further, what we'll do is we'll get into a more detailed model. Okay, so how we saw in the previous models that we have a simple powertrain and we also have a tire and road interaction. So let's get into this one. This is the US city one that we just saw in the starting. So now you see over here, what we are doing is we have this part, which is already there. Then we have a powertrain, simple powertrain that we already explained. And now it is not only just controlling the steering, okay, it is also controlling the velocity. Okay, so for that, what we are doing is we are using a pure pursuit controller block for controlling the steering angle. And then for controlling the velocity or so that it matches the desired velocity profile, in that case, we are using a longitudinal driver, which is just a simple PI driver over here. Okay, just using the PI controller to match the desired drive cycle. And in this case, what it is giving you the acceleration command and the deceleration command, or the throttle or the brake. And then here we have the waypoints. And additionally, what we have done is based on the position of the, or I can say based on the region of the map, or based on the X and Y, we have created a lookup table that, okay, if it is in this region of XY region, it will give the velocity is this much. Okay, so that's what we have kept it over here. So if I just open this, okay, you can see that the velocity is increasing and decreasing based on the XY values. Okay, so this is what we are doing. Okay, and in any case, so this is the whole thing with new things like velocity distribution lookup table and the longitudinal driver. And in here, what additionally we have added is we are now interfacing it with a scene. The scene is based on a US city block. So there are multiple scenes in this block. So this block is called simulation 3D scene configuration. So this block basically configures your Simulink model with the Unreal part. Okay, so that's what we are doing it over here. So there are multiple options. We have straight road, curved road, parking lot, and everything is there. And then default scene, you can get it from Unreal, but Unreal editor, or if you have from Roadrunner, or if you have any exe Unreal, that also you can do. But here we are using the default scenes. Then further, we are selecting a car. So for example, here we are selecting a muscle car. Okay, normal sedan car, I would say, like fancy sedan car, but we also have a basic sedan car also over here. Okay. I have only one screen today, so that's why everything is popping in front of my screen. So I'm having challenge. So anyways, so now you have understood that we had a vehicle dynamics block and then a lateral and the longitudinal controller. Why? Because we want to move fast now. We don't want to move like a robot. And here we are also providing a velocity distribution, which is a velocity based on the XY position. Okay, and the target of this driver is the new driver, which is longitudinal driver, to follow that velocity profile. Okay, so now let's run it and see that what happens. Okay. So I see over here that we are moving much faster and in a city drive. Okay, and here is the result that we are getting. Okay, so you can see that the result is perfect. Now, okay, before I move to the one more interesting part, do you have any questions regarding this? I can also run this with a formula student car if we have. Yes, we have it over here. I don't know if I have to do some settings in this with the FS car. Let's see. Okay, this is your FS car now. So yeah, any questions until now? Okay, if not, I'll also show you some of the other features that, I mean, you can use the model. For example, that if you have to collect certain data from a camera or from a LiDAR. So in that case, again, here you can add some kind of cameras which are already there in the toolbox. Okay, so for example, I'm here bringing a simulation 3D camera. And what I'll do is I will give the output of the image to a video viewer. And further, I want to mount it. So I'll mount it on the front bumper of the car. And then I'll just simply apply and then okay. And further, let's change the car back to the muscle car because it will give you better view. And now let's run this. Okay, so what we'll do is it will show you the Unreal part. At the same time, it will also show you the camera part. Okay. Now, if you have this view from the camera or from the LiDAR, we have LiDAR blocks as well. You can further also try to build your own perception algorithm because now you have a synthetic data. So you can try different scenarios, different conditions, and test your perception algorithms. Okay. Okay, awesome. And also this question also we keep on getting from the students. So for all the Formula student teams, the license that we are providing to the Formula Bharat, so this contains all these toolboxes that I'm talking about today. Okay, any other questions apart from this? I know it's more than 1 hour now, but if you have any questions, you can ask, and otherwise we can just move to the next part. Okay, no worries. Okay. Now, once we have seen the pure pursuit, of course, if you would have seen, the pure pursuit controller is not taking the vehicle dynamics into account. Okay, so that's one of the drawbacks, because if you have very high fidelity model, a bumpy road, in that case, you might face issues while tuning the pure pursuit controller. So one option is that many times what we have seen is that they make the gain adaptive. Okay, so you can also try that. So you can make the gain adaptive. And in that case, you can take into account different bumpy roads, but still, like if it is moving fast, it is bumpy road, and if you have a very high fidelity vehicle dynamics model, it might fail in certain scenarios, but not always. It depends upon how you're tuning it. Okay. Now let's do one thing. We will go to the another controller. So this is very, very popular controller, and this is sort of like also works because it to some extent it is taking into account simple vehicle dynamics model into the controller algorithm. Okay, so this is the Stanley controller. Okay, and this was used back in DARPA Grand Challenge. I think it's way back. I think it was in second or third DARPA Grand Challenge for the autonomous driving. And from there, they built this geometric controller. Again, it does the same thing. The only difference is that here it is based on the cross-track error. Okay, so this is the cross-track error. Okay, so it is not only on the look-ahead distance, but it is based on the error or the deviation that we are getting. Okay, so it is not dependent on the look-ahead distance. So this is the formula, and here I have added the research paper that explains the whole formulation, like how you got this formula for the Stanley controllers. Again, here again, if you want to implement this, this is quite a simple job again, because we have the blocks for the Stanley controller. So if I go into this, the model that we have, let me run this. So in here again, if you see, things are same. The only difference is that here we are using two controllers. One is the lateral controller Stanley, okay, which is basically based on the formula that we saw. And then we have a longitudinal controller Stanley. Now, a longitudinal controller Stanley is, again, it is just it is just a PI controller. So even if you replace this with the previous PI controller or the longitudinal driver, it will work the same. Okay, there's no much difference. In here, the difference is that if you see over here that this is taking into account the dynamic bicycle model. So as I mentioned that it takes into account the vehicle dynamics model, but a very simple vehicle dynamics model takes into account. So here we have options for kinematic bicycle model and also the dynamic bicycle model. And here you can again define different gains, which is there in the formula. And for the vehicle dynamics part, you can see over here that we are asking for the vehicle mass, longitudinal distance from center of mass to front axle, and different dimensions than the tire corner stiffness. Okay, and again, the procedure is same. You have the powertrain, you have the vehicle body, and you have the Stanley controller. Okay, now in this one, we tested the model in a US highway scene, and if I run this, so I downloaded this today when we tuned it using the last version, but still it works fine over here. Yeah. Only that the timing of the brake, I think at the end it will crash to the side lane. Yeah, should crash. Yes. Okay. So yeah. So in any case, like the thing is that to track this trajectory. Okay. So the important thing that it is there is the which type of controller you are using for the steering, and of course along with that how you're tracking the velocity profile. So any questions, like do you have any questions until now, like anything surprising or you're not understanding anything? That I know that the content is like there are a lot of things over here, but anything you have, like, you can also put in the chat if you want. No need to switch on your speakers. Okay, perfect. Okay, so now the last part, I mean, I heard that someone spoke about MPC. So like what advantage will MPC have over these two controllers? Can anyone say that, like, what will be the advantage of MPC over these geometric controllers? I think Kaushik, you mentioned that you have heard of MPC. Like, any thought? Like, what do you think?
Uh, like compatibility, I would say, but not sure.
Okay, no worries. I mean, see the I would say advantage in this case is that it will have a like full vehicle dynamics model into account, and more. I mean, more than that. Okay, let me bring that block diagram that we have. More than that, so it solves an optimization problem at each time step. So when you're running it, okay, when you're running the algorithm while you're driving, so it will each time try to correct that. Okay, so that's an advantage. And the optimization is based on the vehicle model, which is inside that. Okay, so you have a plant model, but you have the MPC controller, which is basically running an optimization problem based on the vehicle model. And also it allows constraints. Okay, so that is also there. So if you want to put certain constraints in the controller, so that also can be done. And then, so it can be implemented on linear and nonlinear models. And however, the problem, I think in the initial part of the session also, I told that the problem here is that it is computationally expensive. Why? Because there's an online optimization going on when you're running the algorithm. Okay. So again, here the implementation is quite simple using the blocks, but I would suggest that if you are very much into MPC, model predictive control, you can, there's a full tech talk from our end, like understanding the MPC concept from scratch. I would say that it's a like I think a series of 7-8 videos. Watch that, and then you like directly jump into these kind of implementations. Okay, if you're a student, like, that definitely helps to understand the concept of MPC, because in MPC the major part of the challenging part is tuning the parameters, because there are different parameters, there are different gains, there are different constraints. For example, let's get into the last model that we have. So let me first run a simple MPC 8-course example where we are just tracking, I would say skip pad, you can say, or you can say just a 8-course. In this one, what we are doing is if you go into the MPC block, okay, so the tuning parameters are like humongous. There's a lot of tuning parameters. First, the constraints that you define. Okay, you define the constraint minimum steering angle, maximum steering angle, acceleration. Okay. And then you have the sample time, you have prediction horizon, you have control horizon, and then you have the weights also you have to define. So this part that you say from model predictive control settings and the controller behavior. So this is a challenging part to tune when you're tuning. Okay. Now, this again, we build the model, okay, based on the 8-course. So this will perfectly track it. Okay, the tracking is really good compared to the Stanley and Pure Pursuit, but on the cost of computational complexity. Okay, so it is computationally expensive. So meanwhile, it is running. I'll do one thing. Let me see. So it is taking 2 rounds in one circle, and in the other circle, it is taking another 2 rounds. You can see over here that this was a reference path, 2 circles for each 2 rounds, and it is perfectly tracking it. Okay. Now, I was mentioning that if you want to learn the whole concept of model predictive control, this is a good series to watch. Okay. You can watch the series, you can understand the concept, and after that, you can also try the models we are showing over here in all of this whole series, because if you want to try hands-on, you can also try hands-on, and then you can get into more some kind of advanced model like this one or the highway tracking. So if I what I'll do is I'll just put it over here. Yeah, and okay, so any question? Okay, before I think if you have any questions, there was one question which initially came. I think it was from Kaushik regarding the code generation. So all the examples that I showed for the pure pursuit, for the MPC, for the Stanley, all these blocks are code generatable. So for all these blocks, you can generate the code out of it. Okay, so you can see over here, you can generate a S function, you can generate code, and you can deploy or flash on the hardware. Yeah. So here you don't have to worry, because all these blocks are, when it was built, these are all code generatable.
Okay.
Yeah. Fine. So just like few, I mean, this was the end of the like whole content. I know I think it's crossed more than 1 hour, so sorry for that. But the whole point is that there are few things when you build some kind of controllers, that first of all, wherever we were talking about the waypoints or the reference signals, okay, the first step should be kind of cleaning that, or kind of doing some pre-processing in that, because if there are certain kind of outliers, if you have X and Y, okay, going from one point, and then again there is a deviation because, or maybe there is some kind of noise, you need to remove that, and then you prepare the reference signal. Okay, and then for higher velocities and varying curvatures, combining lateral and longitudinal controls gives better tracking results. Why? Because you can't move in like sharp corners with a constant velocity. So that's why you saw that in the lateral controller, in the Stanley controller, we had lateral and longitudinal controller. And in the MPC also, when the MPC block was giving us the output, it was giving the steering output, and it was also giving the throttle and the brake command. Okay, so it's better that you do it. And then also, which I have not mentioned, that tuning in MPC is could be quite challenging. So you need to work on that and understand what are these parameters. Like I was talking about the control horizon. Okay, there are multiple parameters which you need to understand, that if we increase this, what will happen? If we decrease this, what will happen? So for that, what we have done is the model that we just ran today, it is on GitHub. Okay, so MPC tracking. So we have also kind of documented it, which will in the README file of GitHub, which will help you to tune the model. You can see that. Okay, so here are a few steps to guide you through the selection of design parameters. I didn't go into detail because we are running short on time, but here I have provided all the details, like how you select the sample time, prediction horizon, what will happen if you change the prediction horizon. These are all in here, and there are certain troubleshooting tips also that we have provided. Okay. Yeah, so just last thing, that MATLAB simply provides various algorithms, and most of these algorithms are code generatable, because if you're working on autonomous driving, ultimately you have to deploy your code or flash your code, because you have to run an actual vehicle. So these are code generatable. Okay. And now, yeah, this is all the racing launch resources. Basically, a point of contact. If you have any queries, if you're from a Formula Student team, you can reach out to us at racinglaunch@mathworks.com. So the thing that we presented today, this is all documented in a form of a technical blog. Okay, so this blog is called Simulating Trajectory Tracking Controllers. It points you to all the videos, to all the GitHub submissions which are there, all the models which are here. Okay, so you can also have a look into this. So it starts with how to form a reference trajectory, what is the vehicle model, and respective video for this. And then for pure pursuit, we have a video. Stanley, we have the same video, and also for the MPC, we have the whole video one. Okay, fine. So any question, you have from today's content, or any feedback you have, anything like if you want to speak out.
Actually, in dynamic disciplines, there are some rounds where we have to take multiple laps. For example, in skid pad or autocross, you have to take multiple turns. And at the time, I heard that some peoples will do the first lap as like a trial, and then based on the memory, they will give attempt for fastest laps. So, like, how do you see that could be implemented?
Could be like, what did you ask last? How it can be implemented in the simulation, is
Yeah,
it?
like how like we have to store this information and to use it in the real time for the upcoming labs. Like,
I think so. So what happens, Kaushik, is that, yeah, I think that's a good point. So first is that in terms of trajectory tracking controllers, if you ask me, okay, so the best strategy is based on the test that you do. That will give you the information that which control is suited for which one. Okay, for example, it might happen, like for example, for simple like the acceleration run, if you want to do driverless, okay, your pure pursuit works, that's fine, right? Okay, it's just going to a straight line. But if you go to the endurance run, it has different twists and turns, so maybe MPC could be better. Now coming to the point that they do the first lap just to test, okay, so basically what they do is that when they run the vehicle or do the trials, the data that they collect, okay, after collecting the data, what they do is they kind of compare it with the desired performance, and based on that they have all different rubrics and scorecard. From there they select okay, that these things we are missing. For example, during the cornering, what is happening, during the straight and what is happening, what things we can improve, what different parameters, or you can say some kind of sensitivity analysis. Okay, so sensitivity analysis will give you what are the different parameters which are sensitive to the lap time. Okay, lap time simulation or the performance of your lap time of the whole endurance run. So if you are able to find those sensitive parameters, you can tune that and then you can have the much better performance. Okay, it is basically how you're logging the data. Okay, so you need to log the data for that when you're doing the trial runs. Okay.
yeah, thank you.
Fine. Any other questions, Mr. Ishant? If you have any question, we don't have many people over here. That's why I'm calling out the name. Sorry for that. So, but if you have any question, you can go ahead. Okay, I think we can't hear you. It's maybe some audio issues from your end, but it's fine. Okay. But if you have any question, you can reach out to us at racinglaunch@mathworks.com, or you can also reach out to Formula Bharat, and they can forward the query if you have any questions. Okay. So in the next session, so we are also left with. Okay, thanks, Ishant. I can see your message now. So next session will be on ROS and Simulink. So I wanted to ask, there was also one session earlier done, I think, by other partners on ROS. Did any one of you attend that?
No, I couldn't attend the previous
Okay.
sessions, but there are recorded sessions which I can refer.
Okay. So I think it would be great if you're attending the next section, before that, if you can watch that. I think there was someone who introduced ROS. There was some partner who did that in the previous sessions, because that will give you understanding what ROS is, that ROS is a middleware and all those things you'll understand. And then in the next session, my colleague Akshara, she will be talking about how to integrate ROS and Simulink. So how you can bring the ROS packs, okay, how you can use different blocks, how you can basically use ROS and Simulink together. Okay, so that will be covering in the last session for MathWorks, I would say. Okay, this for us, it will be the last session. Okay, so yeah. Okay, so with this, I think we're all done. So thanks for joining. Okay, I hope you found it useful, and you can go through the resources. There are a lot of things which we couldn't cover because the topic is huge, and we want to mostly cover on how to implement it in a simulation platform. Okay, so thanks. So thank you, Kaushik, and thank you, Shant, and thank you, I think, other folks who were already there in the call. Thank you so much, and have a nice weekend.
Have a nice weekend. Bye.
Thank you, Veer. I would like to thank you for taking your time to deliver this informative presentation with Alakshendra. And I would like to thank you, all the participants, for joining this evening. Thank you so much.
Thank you. Yeah, thank you, Dikshita. Thank you. Have a nice day.